Hello everyone and welcome back. In this video we're going to talk about continuous probability distributions. When we're working with continuous random variables, we need to assign zero probability to any particular value. So this means that the probability of x equals lowercase x is equal to 0 for any single numerical outcome x. We will use density curves to assign probabilities to an interval by finding the area under the density curve. Now these curves are called probability density curves, and the area under the curve on an interval from a to b represents the probability that the random variable will fall between that interval. Now one kind of probability distribution is called a uniform distribution on an interval from a to b if the density curve is a flat line above that interval. The following example shows a uniform distribution on the interval from 0 to 5. So what we see is that there is a flat line on the interval from 0 to 5, and then it is equal to 0 everywhere else. So now let's use the uniform distribution to calculate the following probabilities. Let's find the probability that x is equal to 1. And so what we want to look for is the area under the uniform distribution where x is equal to 1. But now, what is the area of a line? Well, since the line does not have any width, the area will be equal to 0. And so the probability that x is equal to 1 is equal to 0. So now let's find the probability that x will be between 1 and 3. And so we're looking for the area under the curve from the interval from 1 to 3. And so the probability corresponds to this shaded area. And so the probability will be equal to the area of the rectangle. So we take the base times the height. We see that the base has a length of 2, and the height of the rectangle is 0.2. And so the probability is equal to 2 times 0.2, which is 0.4. So now what is the probability that x will be greater than or equal to 2? So here we want to find the area to the right of 2. And so the probability will be the area of this rectangle, which has a base of 3 and a height of 0.2. And so the probability will be the base times the height, which is 3 times 0.2, which is 0.6. So now let's take a look at another example. Suppose we're given the following probability distribution. So this is a triangular distribution. So let's verify that the area under the probability distribution is equal to 1. So the area under the distribution is the probability that x is between 0 and 2. And so what we want to look for is the area of this triangle. The base of the triangle has a length of 2, and the height of our triangle is 1. Recall that the area of a triangle is equal to 1/2 base times the height. So this is 1/2 times 2 times 1, which will simplify to 1. So now let's find the probability that x is less than 1. And so the area of this probability corresponds to the area to the left of 1. And once again, what we have is a triangle. The base of the triangle is 1, and the height of the triangle is also 1. And so the probability that x will be less than 1 is 1/2 base times the height. So 1/2 times 1 times 1, which equals 1/2. Now let's find the probability that x is greater or equal to 1.5. So in this case, what we want to find is the area of this triangle. So it would be the region to the right of 1.5, and we still have another triangle with a base of 0.5 and a height of 0.5. And so the probability will be 1/2 base times the height. So 1/2 times 0.5 times 0.5, and this is equal to 1/8. Now what is the probability that x will be between 0.5 and 1.5? And so what we want is the area between these two values. And this probability corresponds to these two areas. So what we see is a rectangle and a triangle. The base of both of these objects have a length of 1, and the height of each of these are both 0.5. And so the probability is going to be the area of the rectangle plus the area of the triangle. So we take the base of the rectangle times the height of the rectangle plus the area of the triangle, which is 1/2 times the base of the triangle times the height of the triangle. Oops. And so we have 1 times 0.5 plus 1/2 times 1 times 0.5. and this will simplify to 3 over 4. So here are a few examples of where probability density curves can appear in the sciences. So in chemistry, the Maxwell-Boltzmann distribution is a distribution that is used to determine various speeds of ideal gases. It can be used to calculate the mean speed, the most probable speed, and the root mean square speed. Now in physics, the electron probability density is used to find the probability that an electron will be within a certain radius of the atom. Now returning to statistics, a probability density curve that we have already encountered is the normal distribution. Now these curves can be used to determine the probability of observing certain data. Now recall that we can standardize data so that we can shift the mean to 0 and rescale the standard deviation to 1. So instead of working with just any normal curve with a mean of mu and standard deviation of sigma, we can work with the standard normal distribution instead, which has a mean of 0 and a standard deviation of 1. Now calculating the area underneath the normal curves is rather tricky, and it involves some calculus. Now these concepts fall under a branch of mathematics called integral calculus, and we will be borrowing some results in order to determine the areas. So to find the area under the normal distribution, we'll be looking at using a z-table. And the z-table will show the cumulative area underneath the curve from the interval from negative infinity up to z. So let's take a look at some examples of how the z-table is used. In the first example, we will look at finding certain areas under the standard normal distribution. Suppose that we want to find the area to the left of a z-score of 0.45. So let's first draw our region. So we have a normal curve that is centered at 0. And we're interested in finding the area to the left of 0.45. So here is part of the z-table. Now, the left column of the z-table will show the ones digit and the first decimal place of the z-score. Now, along the first row in the z-table shows the second decimal place of the z-score. And so to find the area to the left of a z-score, which is 0.45, we will first locate the ones digit and the first decimal place in the left column. So we want to find 0.4 in the first column, and then along the first row, we will locate the second decimal place, which is 0.05. And so where they intersect is the area to the left of this z-score. So we can write this as the area to the left of 0.45 is equal to 0.6736. And so this is what our z-table gives us for the area. So now let's find the area to the right of z equals negative 1.80. So let's first draw the region under the standard normal curve. So the mean is 0, and we want the area to the left of negative 1.80. And so we're looking for this shaded region. So we're looking for the area to the right of negative 1.80. So now keep in mind that the z-table gives us areas to the left of the z-score. Now recall that the total area under a density curve must be equal to 1. And because we want to find the area to the right of negative 1.80, and the z-table provides us the area to the left of the z-score, then we can use the complement rule in order to find the area to the right. And so mathematically, what we could do is look at the area to the left of negative 1.80, and if we take 1 and subtract this area, then we get the area to the right of negative 1.80. And so mathematically, we can write this as 1 minus the area to the left of negative 1.80. So now using our z-table, if we look up our z-score of negative 1.80, we end up with the area to the left is 0.0359. And since we want the area to the right of this z-score, we're going to take 1 minus this area. So 1 minus 0.0359 will give us 0.9641. So now let's determine the area between the z-scores of negative 1 and positive 1. Once again, keep in mind that the z-table gives us the areas to the left of z-scores. So how can we determine the area between negative 1 and positive 1? So if we were to look up the z-score of 1 in our z-table, then we end up finding the area of the shaded region plus the left tail. And if we look up the area to the left of negative 1, then we get the area of the left tail. So we can subtract these two areas in order to find the area of the shaded region. And so the area between negative 1 and positive 1 can be calculated by taking the area to the left of 1 and subtract the area to the left of negative 1. So looking up 1.00 in our z-table gives us an area of 0.8413. And looking up negative 1.00 in our z-table gives us 0.1587. And so the area between negative 1 and 1 is 0.6826. Now this area should sound somewhat familiar to you. Recall from the empirical rule, we know that approximately 68% of data falls within one standard deviation of the mean. More precisely, 68.26% of data falls within one standard deviation of the mean. And so the z-table can provide us slightly better estimates for the area under the normal distribution than the empirical rule. Now let's suppose that we have the area under the normal distribution, and what we want to find is the z-score, which corresponds to this area. So we can use the z-table to estimate the z-score by using the table slightly differently from the previous example. So let's determine the z-score, which corresponds to the bottom 0.5% of data. So let's first draw our region. and we'll call the z-score that we're looking for z star. So the bottom 0.5% as a decimal is 0.005. So since we're given the area, what we want to do is look inside of the table for the values that have areas which are closest to 0.005. So looking in the table, the closest values to 0.005 are 0.0051 and 0.0049. So now we will work backwards from our table to determine the z-scores which corresponds to these areas. So the z-score corresponding to 0.0051 is negative 2.57. So let's write down the areas given to us from our table. So the area to the left of negative 2.57 is 0.0051. Now the z-score corresponding to 0.0049 is negative 2.58. And so the area to the left of negative 2.58 is 0.0049. So notice that 0.005 falls right in between these two areas. And so to determine z star, we can take the average of the two z-scores. So z star is negative 2.57 plus negative 2.58 all divided by 2, which is negative 2.575. So now let's find the z-score, which corresponds to the top 5% of data. So let's first draw the region, and we'll call the z-score that we're looking for z star. And so the area to the right of z star is 0.05. So how can we determine the z-score, keeping in mind that the z-table gives us areas to the left of z-scores? Well, we can use the complement rule to determine the area to the left of z star. So the area to the left of z star is 1 minus 0.05, which is 0.95. So what we want to do is look for the two closest values to 0.95 inside of the z-table. So looking inside of the z-table, the two closest values are 0.9495 and 0.9505. So now let's write down their corresponding z-scores. So the area to the left of 1.64 is 0.9495, and the area to the left of 1.65 is equal to 0.9505. So now notice that 0.95 falls right in between these two areas. So we will take the average of these two z-scores to determine z star. So z star is 1.64 plus 1.65 all over 2, which is 1.645. So now let's find the z-scores, which correspond to the middle 95% of data. And so here we're going to have two z-scores. We'll call them z1 and z2. And the area in the center is equal to 0.95. So how can we determine these two z-scores? Well, in order to find these z-scores, we need to determine the area to the left of them. Now, if the area between z1 and z2 is 0.95, then this means that the remaining 0.05 area are in both of the tails. So the combined area of both of the tails is the remaining 0.05. And by symmetry, each of the tails will have half of this area. And so the area to the left of Z1 is going to be half of 0.05, which is 0.025. And then the area to the left of Z2 is going to be 0.025 plus 0.95, which gives us 0.975. And so what we want to do is look for the areas which are closest to 0.025 and 0.975. So looking inside of our table, we are able to find 0.025 exactly. And so now we'll write the z-score, which corresponds to this area. Our table says that the area to the left of negative 1.96 is 0.025. And so this tells us that Z1 is negative 1.96. And similarly, we are able to find 0.975 exactly in the table, and its corresponding z-score is positive 1.96. So the area to the left of 1.96 is 0.975, and so this tells us that Z2 is 1.96. And now these values should be familiar as well. Recall from the empirical rule that approximately 95% of data falls within 2 standard deviations of the mean. More precisely, 95% of data falls within 1.96 standard deviations from the mean. So again, the table can give us slightly better estimates than the empirical rule. And this will conclude our lesson for this video. In the next video, we will look at solving some problems using the normal distribution and the z-table. And I'll see you then.